So that's one of our services, a service that we developed under the DMDI research program called Mind the Gap, for generating new solutions from existing solutions. The second feature of the twin environment we put together, I want to talk a bit more in detail about, is the scientific optimization of the processes. As we were previously seeing, with a real-time model updated, we can understand what's going on in the machine in more detail than was previously possible. If you only have a G code, all you know is you're going to go from 000 to 111 at a certain speed. You've no idea what you're going to do along the way. But if you have a real-time model, you can detect how much material you're going to be removing during that movement, and therefore compute the ideal speed given the current conditions. So the digital twin becomes an environment for writing apps. I can develop an app for that. This app takes the information computed for the machining program and your various policies and decisions, what tolerances are there, when you think it's a good idea to change things, when it should be locked down, what the material is, and what the vendor recommendation is, and can come up with adjustments. And there are different kinds of adjustments. There is the one I'm talking about with going faster, but there's also adjustments because the stock is bigger. The stock may have an additional 3 millimeters on it, for example. If you know that that particular depth at the top is bigger, maybe you can still do the machining, but you need to make an adjustment. And it could be an app for that as well. So this is connected to the operator via the smartphone. It enables the adaptive programming, and it has some quite dramatic results, as we will talk about in a moment. We have two experts on optimization in the room. At the back there's Leon Zhu, who is the Boeing expert. He's so good that we're not allowed to even look at what he's got. But Sandvik is one of the world's biggest vendors of machine tools. They too know an awful lot about how to use their cutters most efficiently. So I'd like to welcome Bengt Olsen, who will talk about the principles behind this kind of science.
Thank you. So I'm Bengt Olsen from Sandvik Coromant, and I'm also part of the working group 15, Digital Manufacturing, and has been that for a long time before we had that name. And I'm just going to show the principles for what's included in the demonstration today that we have seen. And we concentrate on the chip generated, and since I'm from a cutting tool company, concentrate on what's happening with the cutting tool. And today's demonstration that we saw shows how a request from our cutting tool to run at constant chip load can change the behavior, or it's requesting the change of the behavior of the machine tool that's driving the process. And I will show some quick theory. I'm not going to do a full explanation about milling. But chip thickness, even if we drive the tool with a constant feed rate, depending on how much the tool is engaged, in this case it's a radial engagement, the chip will become thinner the smaller engagement is. The same thing happens if you machine at a smaller depth of cut, where on the radius the chip will also become thinner. These effects are included in this demonstration, in this logic. And it's Leon Zhu and myself that have developed this little black box, since we cannot show everything we know Those are our company secrets. So how did we do this? We have the real process that we have seen on the video there. We developed, or Martin has developed the digital twin. And they exist at the same time, real time. So what we do, we get information from this digital twin about the cutter and workpiece cross-section information. And our logic here is figuring out the chip thickness and requesting a feed override to the machine. So if the chip thickness is predicted to be smaller, it will increase override. So this is the idea behind it. So very simple. Okay. And I can also say one thing. Now we have to deliver. I mean, in the past we have to deliver the tool to the customer. Now we have to deliver the tool 2 times. Okay.
So you can charge twice as much for it.
Of course.
So can you share about that? Are you going to share about how you have to deliver the tool 2 times, right? The digital. Do you want to talk about that?
I can do that. Today we have about 80% of our tools. We can receive them as a digital package with 3D models and also the parameters. Parameters specification comes in an ISO 13309, the cutting tool standard. And the 3D models are today 8203 or 214. Tomorrow maybe everything will be 242. Yes.
This is Noah's question. What would cause the cut part to vary from the plan for machining such that you could adjust the
It's whatever happens before. So the tool before or the raw piece. That was the case in this demonstration. Each part had different heights.
Let me bring up a car driving analogy. Supposing I have to drive from here to Portland. If I've got to get there urgently, I'm going to put the pedal to the metal and really run for the gas and do everything within the legal limits, which is the tolerances. On the other hand, if I don't have to be there until late tonight, I want to save gas and save wear and tear on my engine, so I drive gently.
So there's a plan, a program for the speeds and feeds and cutting tool paths before you start.
Right, and that assumes a particular speed. That assumes you're always going to go to Portland at 60 miles an hour, no matter what.
And so this is taking feedback of where you actually are.
This is saying it's urgent, so I'm going to go at 70,
Right. So what would
or
cause
I've got
where-
lots of time, I'm going to go at 30.
What would cause where you actually are to be different from where you expect?
What could happen is that you used another tool to machine the surface before. And then my tool will say, I still want to have the same bite into the material. And therefore it would tell the machine, you need to run at 150% now. Or slow down to 50%.
And what happens is just stuff happens.
Yeah.
Suddenly your part, which wasn't urgent, is urgent because something else broke down.
Are you actually monitoring the spindle load to determine what the cutter load is, the chip thickness, or? what-
We're not using that data today, but we certainly can do, yes. That can verify that everything is correct.
Hedge. Hey, so sometimes what we see too in machining is that we'll have a forging, and that forging will be, approximately correct. So one thing I would think you could do with this is that you could model the actual forging that was on the machine. You could probe the forging and then gather your cutter engagement based on the actual stock that's on the part. The other thing is that when Boeing buy aluminum from suppliers, we pay them by the pound, okay? And we give them a tolerance and saying this could be 1 inch, between 1 inch and 1.1 inch thick, and we pay them by the pound. And so you can bet that our stock is frequently on the thick side.
Question.
Oh, okay.
Is real-time measurement of removal amount is included in your system? In order to guarantee stable machining, you should know removal amount
No,
in
no, we
real-time
don't.
manner.
This demonstration is not calculating that, but it's the information is there to calculate that.
Yes, we are calculating.
Yeah, you have the area.
We are computing the real-time volume.
Yeah. You're right.
Yeah.
We have the cross section between the cutter and the material, and we have the
Yes.
feed.
Okay, thank you, Banks. Okay, so the last thread of our demonstration is it's good being able to make all these changes. The big changes to get a much better process, the smaller changes to adjust to the current schedule, the actual stock, etc. But while you're doing all these things, you've still got to make something that the customer can use. And a key thing about the digital twin technology is that we are making a real-time model of what's being machined, and therefore we can measure that model. And we measure that by exporting step from the digital twin, step AP242, to a metrology service. And we're going to be showing two forms of metrology today. Traditional metrology is done on a CMM machine, and we have one in the basement. And as soon as we've finished upstairs, we're going to go downstairs to that basement and watch the machine measure the physical part, copy of this, in the room there, and we'll see the automated construction of a measurement plan for checking the tolerances as described on the part in AP242. More futuristically, upstairs we're going to take a look at supposing I did the measurements in real time. Supposing what I just showed during the machining, the development of a snapshot of the current state of the model. Sending that into metrology software so that it can evaluate those results and let me know if I'm going to meet my tolerances or not. Eventually, this may lead us into what's called closing the loop. Machining, measuring, adjusting, machining, and measuring. For the moment, we'll just take a look at the requirements in 242, the results as STL, and a basic comparison to produce a model of the difference. So I'd like to invite Andy of Montoya to give us that demonstration.